Okay. Shared screen. Yep. How can I make this small? Ah, yes. Okay. Okay, here we go. Our new subject is trust systems. Just a second. Trust systems. Okay, why we use these trust? Oh, by the way, what is a trust system? Let me show you from Google. Whoop. Take this out. Just a second. Trust is okay. Basically, here. Okay, let's open this page. Here there is a sketch regarding a trust system. Let me see that sketch. I'm gonna explain it. Where is, yes, this is a trust system, as you can see. Trust, why we are using this trust system? Okay, if we are running a large distance, we have to use a beam. So a solid beam, for example. So as an engineer, we have to do our designs in an economical way. So if we put a solid beam, maybe steel, maybe timber, whatever, we have to use more material. But here, what we are doing, we are using, as you can see, these straight members with bracings and vertical posts.
Hocam, we can't see what you're showing. We are just
really
seeing
okay.
trust system.
Oh, I'm sorry.
Writing.
Okay, just a second. Stop sharing. Share again. Can you see now?
Yes.
Okay, I just Google it. Okay, this is the first thing I found in Google, but that's good for us. Okay, let's go back. Okay, why we use trusses? Okay, if we are bridging a large span, we have to use a beam system. So you are gonna do a roof, like a large area. You have to put a beam on top of the columns. So these columns or beams, solid beams, will be very large. And this is not an economical design. So we have to do all these calculations in an economical way. So engineers found this method to make an economical design. Actually, if you look at the history of this trust system, it comes from Romans. There are simple examples in ancient time, in Roman time. So here we have a truss system, as you can see in this part. What is this? Instead of a solid beam, we have a beam system. But when you look here, you can see all the beams are, all these beams are very, very straight. And this mid portion is connected with the bracings, diagonal members, and with vertical members. So instead of to use a big, large section, we can carry all these loads with this light system. You can see the white areas are openings. There is nothing here. our structural members are only these red members here. So we use this system generally everywhere, but in generally for the roofs, for large areas. If you are designing a hangar for a plane, so you have to breach more than 100 meters. Your roof span will be a large span. So, for example, more than 100 meters. You can't put a solid member there. You can't carry anything with a solid member, because you have, if you do a solid beam there, you have to put a large and a big section there. It's not economical. At that time you have to pay more. It's not an engineering. So here we use this system. At the top there is a roof example. As you can see here, if we put many trusses next to each other, as you can see, we make a roof system. This is, at the bottom you can see one truss system. It's a plain truss. And here at the top you can see a roof system. You're using, for example, in this example, 7 truss system in this roof, and you connect these trusses with stability members and purlins. So this is a roof truss system. I'm just talking about what the truss system. Okay, I will show you different examples. Let me see another truss system. Okay, at right hand side, okay, I'm just searching in Google again to show you different types. I'm gonna draw a few, but oh, there's a problem here. Can't see. Go back. Is another truss system an interesting system? Yes, this one. Here we go. Okay, at the right hand side you can see truss systems in real life. For example, this is a railway bridge. As you can see, this span is a large span. So can we put a solid beam here? Yes, of course we can put, but we have to pay more at that time. At the beginning of this course, we talk about the structural system. What was a structural system? Structural system is a kind of system which contains less material. And at the same time, with this less material, we try to carry more load. Okay, that's why these type of systems were found. Okay. Here are the, let me write truss roof systems. Maybe they are more architectural designs. Yes, here we have timber examples, as you can see in Google. At the right hand side, you can see different types of truss systems. In your, actually, these are not the constant things. You can change it. But there is one rule, I will explain it. I'm just talking about types at the moment. You are architects. So at the end of the day, if you like to design anything else, roof system, a sculpture, I don't know, a bridge, all these are possible. You can change these systems, but these are general examples used in the professional life. If you Google like truss roof system, you can see different types of truss systems here. Okay, let's go back to our page. Stop share. and share screen again. Okay, why we are use this truss system? We would like to do economic design. What are the members of this truss system? What we are using? We use straight structural members. Okay, so here we go. If this is a roof system, for example, okay, I couldn't draw a symmetrical system. I'm sorry. Okay, this is a truss system. All these members are straight members. This is the top chord, how we call these members. This is top chord, üst başlık. This is bottom chord. And these are diagonal bracing. These are the vertical posts. Okay. Okay, these are the members of the truss system. Okay, now you can imagine truss system. Let's talk about some rules regarding truss systems. Okay, the first thing is the connection points of these truss systems. For example, this point, all the members connected to each other at this point. That's okay. This point is a hinge. We don't carry any moment at this point. Hinge means there is no moment, zero moment location. I mean, so our members like this, a member with hinged end. This circle is hinge. Okay, hinge is in Turkish mafsal. So no moment or zero moment location. No or zero moment. Okay, whatever. How do you call it? So what we know here, all these members have hinges at two ends. Okay, the first thing is this. All members have hinges at their both ends. Okay, we know this one. So when we connect hinged member to each other, okay, I'm gonna ask you a question. This is a simple question for you. And this is important to understand what we are doing, why we are putting bracings, vertical post, top chord or bottom chord. Here, I'm gonna draw you. Let me change color black. Okay, if I have a structural system with hinged corners, as you can see. In these hinged locations, the members can rotate easily. Okay, there is no moment there. There is no support, resist that rotation. So it can rotate at these circle points. Up, go back. And this one here, we have a pin support. We have a roller support. If we apply a lateral load this system, how this square system behaves? What do you think? How it deforms? Can we carry this lateral load? If we understand this logic, it's easy for us, everything. The other thing is just calculation. If we apply this lateral load to this rectangle truss system, okay, this is a truss system. As you can see, all the members are straight. They're connected to each other with hinges. That's okay. We apply a load. Okay. How it works? Any comment, any idea? We can wait more. Are you sleeping, guys? Okay. Let's do it like this. Okay. Özge Eren, do you have an idea? Are you there with us?
Yes.
Okay. What do you think? There is no correct and wrong or wrong here. We are just talking. If you have an idea. Yeah, I have to this in Turkish first. Maybe you didn't get. Bu sistem arkadaşlar köşesinde mafsal var, dönüyor. Bu gelen yatay yükü taşır mı? Taşıyamaz mı? Taşırsa nasıl taşır? Bunu soruyorum. Yorum. Sadece sohbet ediyoruz. Okay.
Hareketli olduğu için gelen yükü taşıyamaz sanırım.
Okay. How it behaves. Tamam, doğru söylüyorsun. Nasıl, ne olur? Ne olur?
Yani hareketli olduğu için hani denge olmayacağı için taşıyamayacağını düşündüm ama.
Hı hı. Okay. What Özge says due to this or since this system is a movable system, why? Because we have hinges at the corners. This system doesn't carry the lateral load. Okay, according to Özge, she's right. She's right and wrong actually. She's at the midpoint. When we take a look this system, okay, each corner here is hinge. Okay, hinge. So the other members, straight members, they don't deform. So when we apply this lateral load, it's gonna get this shape. Straight members are still straight. This is the hinge point, but there will some rotations on this. No. Okay. This rectangle will get this shape, and during this loading type, it's gonna get this shape, and at the end, it's gonna fall down. So, okay, we are providing each rules. Okay, straight member, hinged connection, that's okay. We are using less material, but our system is not safe. Why? That's the problem. That's the main problem. So we have to solve this problem. As an architect, you have to know this rule very well. Okay. If you are designing, a rectangular shape is not a stable shape. When you apply a lateral load, it gets a diamond shape, as you can see in red line. It gets a diamond shape. after you increase loading, it falls down because, you know, it goes, like at the end, it falls down. This is not a stable system. We have to carry the load in our initial position. So we know that rectangular shape is not a stable shape. We have to convert this something. How can we do that? Okay, let's draw this rectangle here again. Okay, this is our rectangle again. My drawing is not good screen, sorry, but you get the point. So again, we apply this load to top. Okay, if we divide this rectangle, if we add something, for example, if we divide this rectangle to triangles, if we add this red member here, what do you think? Does it work? Yes, it works. What we did here, now the system doesn't get this diamond shape. It's gonna stay as a rectangle under this loading because of this extra member. So as an engineer in truss systems, we don't like rectangles. So the rectangle is not a stable shape. We should use triangles. We have to divide our system small triangles. So here, as you can see, what I did, I split this rectangle to 2 triangles, as you can see. So the load comes from here, basically, and goes down from here to support. Okay, let's change the problem again. Again, we have this rectangle with hinged corners. Here we have a force here. Let's change the bracing orientation. Put it here. Okay. Again, we split the system 2 triangles. It works again. The load basically goes there. This point wants to go in lateral direction, and there will be a tension on this bracing and transfer all these loads to this support. So at the end of the day, what you are gonna know here, we have to divide our system to triangles. Okay, in your projects, sometimes before this COVID issues, I was walking around the garden in the school. There are some sculptures you do in your projects. For example, you are doing I don't know what are the purpose of these members, but there are truss systems, the aluminum members, timber members in the garden. I don't know if they're more at the moment. Sometimes what I see there is a space truss. Space truss is a kind of 3-dimensional truss. When I look there, the students made a truss system and there is no bracing. All the truss system made by rectangles. So this system moves laterally in some direction. You can see some of these sculptures which are connected to trees to get stability. The main problem is this. If you are designing anything in your school projects, in your professional life, you have to divide rectangles to triangles, okay? This is a must. If you don't do that, you can't get a stability. You need, at that time, you need an extra support, like a tree in my example. Okay, I guess you get this point. This is really important. This is important than the calculations. As I explained at the beginning, you're not gonna do these calculations. You're gonna do only simple calcs in your professional life if you need. But in your school life, if you don't do this, you need a tree. So please keep this in mind. Okay. Other,
Hocam, can I
yes.
ask something?
Yes, please.
What if this was a square? Would we still need a triangle?
For a square,
Yes.
yes, we need always triangles to have a stable system. Okay. Otherwise, rectangle or anything else, if you have, for example, sometimes in designs, there are some bridges like this. It's like a half circle or less than half circle, I don't know. So if you're doing a truss system, you need these bracings that makes these spacings triangles. If you have a square, every edge equals to each other. Again, we need a bracing member. So we need triangles. Okay. So we have straight members. All ends, two ends of these straight members are hinges. Okay, hinges. There is no moment at these ends. That's okay. We need triangles to get stability. And the other thing, let me open a new page. How we load these truss systems. Oh, just a second, there's a problem on my pen. Yes. Okay. Here we go. We have a truss system again. Let's say we have a rectangular truss. Let me draw a symmetric system. Okay. Let's say this is a kind of roof. You have to know again this as an architect. Okay, this is my truss system. Okay. All the members are straight. Okay. You can see these points are hinge points. We know that. When we look the system, okay, we don't have any rectangle. As you can see, all these are triangles. It's perfect. Now, we need to talk the loading. Okay, in truss systems, we only load these joints. Oh, this one, these points. We only apply loads these points. Okay, these joints. You can put a load here. You can apply any load here, here, here, whatever. Okay. If you apply a load to here, no, we don't apply any load to these members at the midpoint of these members. We only add our loads to these joints. Okay, this is the rule. Why you need this? Okay, maybe you designed this roof or not. You are working as an architect in a shopping center. Okay, for example, if you go to any shopping center, all the shopping centers are decorated for New Year at the moment. So there are some heavy decorations which are applied to, which are connected to the roof. If the roof there is a truss system, as an architect, you have to connect these. For example, we have a decoration here, something else, I don't know. You can't connect this directly to the up to the midpoints. No, you have to do this. You have to connect all these members to these joints. We only transfer the loads from these joint locations. Okay, don't forget this one. This is important. If you do this, if you did this, for example, you can say that, oh, I don't care the rules. I can put this member. I can connect my member to the middle of this member. If you do this, you can break this member down. So it depends on the weight. That's okay. But you apply a load which is not considered in design. As an engineer, we only transfer the loads from the joints. So our structural members, these straight members, carry only axial force. Axial force. If you apply your laws to these joints, okay, you have only axial force on the members. But if you apply this member to the mid of a member, you apply extra moments to these members. Moment. So when you apply load here, your member will get this shape. So it fails your system. We always apply loads to the joints in truss systems. Don't forget this one. This is a must. This is an important rule. You don't have to design this load, but if you are applying anything, an existing truss you didn't design, you have to apply loads to joints. Okay, don't forget this one. Sometimes in, do I have that example? Just a second. Stop sharing. I'm gonna check something. If I found it, I will share it with you. There is an example. These are more important than the calculation, actually. Yes, here. One. Do I have a presentation regarding? No, I don't have any photo. Okay, let's go back. I'm gonna draw it. Share screen again. Okay, in timber houses, you're gonna see this type of, you're gonna see this type of roofs like this. Sometimes you have very small members, but this type. So on this roof, what we put on top of these roof, we put some purlins. Purlin takes the roof cover load and snow load or any load on top of the roof, takes the load and gives these loads to the roof system. Purlin is aşık in Turkish. You know what aşık? Do you know what aşık is? I guess you know. We put some rectangular beams runs between roof trusses. Okay, so on top of these purlins, there is a roof cover. It goes down to the other side. This is the roof cover. So this carry the load. For example, if snow load comes on top of this roof, it takes the load and gives here. And this purlin beam, this is a kind of beam between the truss systems, gives this load to the roof system. Okay, you can see this is a common system in especially timber roof systems. What is the wrong here? When you look at the sketch, there's something wrong. What's it? What we said in the sketch at the left-hand side, we said we only apply loads to joints. But here, as you can see, there are some purlins at the midpoint of the members. There's no joint here. Here, here, here, here. These points are problems, but still, especially in truss systems, you can see this system. Generally, what they do, they generally select a large member for top chord to carry moments, but keep in your mind, this is not true. Okay, someone can do that. That's okay, they can do that, but this is not true. Just I'd like to give an example, a common wrong thing for you. This is wrong, but people use this system. I guess these roofs, timber roofs, are not large, for not large spans actually. It is for 8 meter, 7 meter, sometimes 10 meter. It's not for 25 meter or 30 meter or 50 meter. Okay, so this is wrong, but in professional life, you are gonna encounter this type of details. So, okay, we talked about the rules regarding the truss systems. These are the rules. Now, what we are gonna do next? Yes, let me check my notes. Let me write the rules here again. Okay. Rules. Okay, the first thing is all the in plain trusses here, all members are in the same plane. Okay. The other thing is here. The loads act only to joints of truss system. I've just explained this one. trust members doesn't change their lengths. Okay, they don't change their lengths under loading condition, and the there are hints, 0 moments, that mean hints at connection points. Connection points or joins of members. Okay, these are the rules that I tried to explain. In a trust system, we have 2 different loads. Actually, as a load type, there's only 1 load type. There is only axial load on these members. What is the axial load? What is the axial load? Let me draw it. There is only axial load. If I have a trust member, okay, I take this member out from a trust system. This is a member. This is the length of the member. If I have a load in this direction, what is this direction? This direction is by the way, this blue line is axis of the member. Okay. So if we apply a load in the direction of this axis, this is an axial load. Okay, this is axial load. Axial load. So if this axial load squeeze the member, as you can see, in each side, you can see we have this member, as you can see, this is my pen, and I squeeze it. This is a compression loading, compression, basınç yükü, compression load. We squeeze it. This is a compression loading. Okay, let's change the, again, loading here. If I stretch it, if I try to stretch my member, okay, if I try to take this point out, so this is a kind of load, axial load, that's okay. But this is a tension load, okay. So the main differences between compression and tension is this. Compression tries to squeeze something, and tension stretch it. Okay, this is the main differences between the this loading system. Okay, other rule. Okay, we design a trust system. So there is one more thing we have to follow. There is a simple equation. Let me draw an example here. For example, this is again a trust system, and here we go. We have okay, we have a trust system. So to define this trust system, to make a proper trust system, we have to provide an equation. The equation is this: S equals double D minus 3. What is S? S is number of members. D, number of nodes or joints, but including supports. Okay, support points are also a joint for my trust system. Okay, let's check this for the given example above. Let's find S. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. D. Let's check the joints, including support points. 1, 2, 3, 4, 5, 6, 7, 8. Eight. Okay. Let's do this equation. S 13 equals 2 times 8 minus 3. Okay. This trust system works well. For each our trust system, we have to provide this equation. As I said to you at the beginning, you can design any other shape of trust systems, plain trusses. That's okay. But you have to provide this equation. You have to, after you design it, you have to count the number of the members, then the number of nodes, and check this equation if it works or not. If it doesn't work, you have to provide this equation. At that time, it works like a proper trust system. Okay. Any question regarding this equation? This is basic. We only count the number of members and nodes. That's it. We don't do anything more. Okay, you get this point. We talked about the, yes, we talked about the compression and tension loading. We will go to the, yes, calculations actually. Now in this part, we are going to talk about the trust systems with some loadings. So under this loading condition, we will calculate the member forces. So member forces means here axial loads on these truss members. You know, there is only axial load on these members according to our assumption, our rule. There's only axial load. That's why we only apply our loads to these nodes or joints. We never apply, or we never accept as an engineer to apply a load to midpoint of these members. Don't forget this one. This is really important. You will see these different types of applications in your professional life. Maybe you will be controller for these type of applications. At that time, you are going to say, no, apply loads to joints. That's it. Now we will start to make calculations. We have two different methods. Method of joints and Ritter's method. Let me check a basic example for it here. I have different examples, but yes, this one. Let me write calculation of member loads. 1, 2. We have two methods. Method of joints. Ritter's method. At the end of today, two methods make same thing, but they have some advantages according to each other. We will see it. Let me find. I'm just trying to find an example here. Okay. Or method of sections. Let me write. I forgot it. Method of sections. Okay. Okay. We are gonna do an example on the firstly on about the method of joints. Let me find. Yes, I just found an example. Okay, good. I will explain this method with an example. You have to know about methods in this course. Okay, method of joints. Actually, in 10 minutes, I guess we are gonna do a break. Let's do the break now because I don't want to split this part while I'm explaining. So let's have a break. It's what time is it? 10 plus 5. Okay, we are gonna be here at 10:35. Okay, 10:35, and then we will go ahead these subjects. Okay, see you guys. Play, share screen. Okay, the first method is method of joins. Okay, let's draw an example here in black. Here, I don't remember we have. This is the vertical. Okay. Sorry. Okay, dimensions are 3 meter. Okay, here we can see a truss system with given loading system, and you can see all dimensions. The question is, what are the internal force on each member? Okay, let's give name to these. This is A, B, C. This is D. Okay. Actually, the main differences between these two methods is if we are seeking the each member forces, we use method of joins, or maybe you need only this force, this member's force. At that time, if we are looking not all the members' forces, if we are just looking one or a few forces, at that time we use method of sections or Ritter's method. We cut the system from where we are looking for the force and then write the equilibrium equations. Okay, this is the main differences. Now, what are we doing? We are doing the all member forces. We are going to calculate all member forces now. So that's why we are using method of joins. Okay, rule of thumb. If you get a structural system or a truss system, to start the calculation, what we do first? What we do first to start the calculation? Okay, go back to support reactions. When we get a system, we always first calculate the support reactions. Okay, that's important. After we calculate all these support reactions, then we can go to the member forces, member force calculations, whatever. Here, let's do the support reactions. Here we have a pin support. You can see here vertical A. Also, we have an horizontal A here. Here, this is roller support. There's spacing between the triangle and this line. So this is vertical B. Okay, let's calculate the support reactions here. Okay, let's write total X. Total X is 0. I think I assume that you all know how to calculate support reactions. Total X. I have HA on the system. Is there any lateral load on the structural system? No. HA is 0. Let's write the total MA. Let's calculate the total MA equals 0. MA is this point. Let's do this calculation. Vertical B rotates the system in this direction. Let's assume that this is positive. Vertical B times what? 4. And 5 ton is in negative direction, minus 5 times the distance, which is 4. And here we have 3 tons. 3 tons is in negative direction, minus 3 times the distance. What is the distance? 448 meter equals 0. Okay. According to this calculation, you're gonna see the vertical B is 11 tones. Let me check it one more time. Yes, 11. We know this one. This is 11 tone. No, we are gonna do the total MB equals 0. So for MB, we are here, vertical A times, let's say this direction is positive, vertical A times 4, and then HA times 3, but HA is 0, that's why there is no coming moment from HA. Okay, here 5 tones. 5 tone is in the same axis with the point B. That's why its moment is 0, because the distance is 0. Let's do it. 5 times 0. And here we have 3 tones. 3 tones rotate the system in this direction. When we compare with the first assumption, it's in the positive direction. Here we have 3 times 4 equals 0. So this is 0, you know. Here vertical A times 4 equals minus 12. So here vertical A equals minus 3 ton. Okay, these are the support reactions.
Somehow 3 is positive.
This one, this 3.
Yes.
Okay, what we let me change the color here. For total MB, what I assumed, I start from the vertical A from here. I assumed this direction is positive. Okay, so I write here vertical A times 4. That's okay. So there is no moment coming from 5 ton. You know this one. No, 3. 3 rotates the system, as you can see, in this direction. Can you see this direction? Yes. When you compare this direction with this one, they are in the same direction. So that's why it's positive. Okay. So if we do all this calculation, yes, we have all these support reactions. Vertical A is minus 3 ton. That means the actual direction of this vertical A is in the opposite direction. It goes downwards. Okay, but I don't change anything. I can write here minus 3. No worries. If I take into account with minus, there is no problem. This minus shows the direction, remember. Okay, we have all the support reactions. What we are gonna do in the next, we will take out each joint one by one, and then we are gonna write the equilibrium equations for each joint. So we are gonna calculate the internal forces on the members. Okay.
Hocam bir şey sorabilir miyim?
Yes, please.
Bu VB yükünün nereye doğru döndürdüğünü, yükünün diyorum, hani nasıl anladık tam olarak?
VB. Hangisinde? Şunu yaparken mi?
Evet,
Hangisi?
hani
Şöyle.
pozitif ya da negatif neye göre dedik?
İlk başta kabul yapıyorum. Evet. Ben bu tarafı artı kabul ediyorum diyorum.
O tarafa doğru döndürdüğünü
evet, şimdi kabulüm buydu değil mi? Yönüm bu. yukarı doğru gidiyor.
Evet.
Nokta da şu. Döndüreceğim. Rotasyon noktası bu. Çünkü A'ya göre alıyorum burada. Dedim ki ya bu taraf pozitif olsun. Döndürdüğü yön.
Tamam tamam anladım.
Hani
Teşekkür.
buna göre diğerlerini organize ediyorsun. Tamam. Okay. Now let's take out the joint A. Joint A. Okay, joint A is here. If I draw it here, joint A. Here you go. And what we have, vertical A minus 3. You can write it here with like this, minus 3, or you can directly put arrow like this and 3, whatever you like. Let's change the direction. I don't want, okay. I don't want to change direction. It sometimes mix everything each other. Here, this is minus 3. Okay, by the way, go back. Okay, what we have here, here, let's say we have this member is AC member, F, AC, I write. And here, this is FAB. Now, I take the joint out. I'm gonna write the equations, equilibrium equations, but what should I do first? I have to assume the directions of the unknowns. For example, I don't know FAC and I don't know FAB. Okay, I don't know if it is a compression or tension. In our calculations, tension is positive, compression is negative. Okay, if I don't know if this FAC a compression load or tension load, I don't know. It's same for the FAB, as you can see. That's why I make an assumption. If I don't know a force, I always accept that a tension force. Okay, tension force. So that means it's positive. But this is an assumption. At the end of the day, at the end of my calculation, if I get a negative value, that means it's compression. Okay. So this is my assumption. By the way, this is the joint. If we go out from the joint, this is tension, okay. Tension and positive. If your force goes in the joint like this is compression. And it's negative. Here, I don't know if it's tension or compression. That's why I made an assumption. I said that all these forces goes out from the joint, so they have tension, they're positive. Okay, so let's write the equilibrium equations. Let's write the total. Let me see. Yes, total Y. Here, what I have in this direction, I have minus 3. So I need the vertical component of this AB, FAB. So there is an angle here. So angle is here. Okay, let's say alpha. Dimensions are all here. 3 meter, 4 meter, this is 5. we can, this component is FAB times sine alpha. Sine alpha is 3/5. Okay, according to this triangle given. Okay, let's write it. And this one goes down minus FAB times 3/5 in the vertical direction. There is no more force here, equals 0. So from here, if you do this calculation, FAB, let me check, FAB, FAB minus, let me check, all these are positive, -5. Okay. Is this clear? So FAB is -5. That means FAB actually is not a tension force. It's not like this red arrow. It goes into the joint. But no worries. I can accept like this. I can accept it's in this arrow direction. That's okay. But I can use the negative sign here. Okay, let's do the total x is 0 for this joint. Total x. Here, what we have in the x direction, I have FAC. FAC. Okay, that's okay. And also I have FAB times cosine alpha. FAB is what? -5 times cosine alpha, cosinus alpha, sorry. Cosine alpha. Here, 4/5 equals 0. What we have, let me check the solution here. What's wrong? -4, 4. Okay, it's correct. FAC is -4 ton. Okay, we have just completed the first point. Is this okay? Any question for the first point? I guess one by one, we are gonna take out the joints and then write equilibrium equations. That's it. Okay. Can I take? Okay, I can't take this to other page. I'd like to see the sketch. Okay, let's do point B. No, there are 3 members in point B. 1, 2, 3 with angles. Point C is easier than point B. Let's do first C. joint C, because it's like a joint. Okay, I know this force, this one, FAC. What is FAC? 4 ton. 4 ton. It's, what is this? It's positive. It's tension. It's tension. Tension means goes out from the joint. This is 4 ton. We don't know the other ones, this one and this one. So if we don't know them, we accept their tension. They are going out from the joint. We don't know what are they. So this is FCD, FCD and FCB. And at the same time, we have an external force at this point, external force. This is 5 ton. So in this joint, this is the joint C, and this joint, let's write the total X. If we write the total X 0, here we have minus 4 ton, or minus 4, plus FCD equals 0. I'm just writing this equation in X direction. So as you can see, FCD here is 5 ton. So it's also tension. Here we go. We have a vertical direction. Let's write the total Y0 in vertical direction, minus 5 in the negative direction, minus FCB equals 0. Here, FCB is minus 5 tons. Okay. So we have all these FCD and FCB forces. Then what we have, we can do joint D. Actually, if now we are just talking about the method. You are aware of this method in the first time. It looks really complicated, but if you do some practice by yourself, you're going to see this is really easy. You are not doing more anything. You take the joints one by one out and write the equilibrium equation. The equilibrium equation means here total X and total Y is 0. That's it. It's not a moment equation. Okay, let's do joint D here. Joint D is here, like here, D, and we at the top we have FCDs. We know FCD, which is 4 ton, and there is an external loading here. By the way, let me clear this part. 3 tons. There is an unknown here, this one, which is FDB. FDB. So we don't know this one. That's why we assume it's a tension. The arrow goes out from the joint. Okay. Here we have an angle. Let's write the total Y. It's too easy. Total Y equals 0. So 3 goes down, minus FDB times sine alpha. What was the sine alpha? The alpha is here. Is it same? 443. Yes. This is like alpha. It's sine 3/5. 3/5. 3/5 equals 0. FDB equals minus, I guess it's -5, right? Let me check it. Yes, it's -5 tons FDB. As you can see, there is only one unknown here. So what we have just completed each point and each members. So if you like, you can make a control. If you write this equation on joint B for check, for control. Okay, you can write it. It depends on you. After you calculate each internal force on the members, we have to prepare a table. Okay. For example, what are the members? Let me write them. FAC. Let me do it here. FAC, FAB, FCD, FCB, and FDB. We have a table. This is tension. This is compression. Remember, tension is positive, compression is negative. Okay. Let's write the members on this page. This is 5 because negative is here. You know, the minus shows its compression. FCB, CB here 5, and then FCD 4. Let's go back. FAB -5, AC 4, AB 5. This is just a second. AB 5, other 4. This is 4. This is 5. Okay, this is my force table. After I calculate each load on the members, I draw this table to trace the forces easily. Otherwise, we can't see all the forces on the table. Okay, here what we did, guys. We are using method of joints. That means when you get the structural system, first to calculate. That's not in this rule. If you get a structural system, first to calculate the support reactions. It's a rule of thumb before we start our calculation. After that, one by one, we take out the joints of this truss system and write equilibrium equations. Okay, equilibrium equations. And then when we take these joints out, if we know any forces acts on this joint, we write them there with their sign. If we don't know any internal force, we make an assumption. We always assume their tension. Okay, so we assume they're positive. We write the equilibrium equations for X and Y directions, and then according to these equations, we calculate the unknowns. If we get any unknown, which is assumed like tension at the beginning, a negative value, that means my force is not a tension, it's a compression force. Okay, I accept that minus sign, no worries. And in my table, I write it to compression side. That's it. I think you get the point here regarding the joint method of joints. Today, I'm just explaining the methods. Next week, I'm gonna do some more examples regarding these calculations. We are going a little bit slowly today, and we are doing very, very simple example to explain the concept. Any question regarding this method of joints? Any comments? Anything else? No, I think. Let me find a basic example for the method of method of sections. Sorry, I'm just trying to find a simple example. It's okay. Hmm. Okay. It's a basic example. So okay, let's do this. Okay, next page. Okay. Here we have a truss system again. Okay. There's something wrong with here. Okay, here we have A, B, C, A, B, C, D, E, G. Let me change C here. C. Okay. Oop. Where is it? This one. This one. And this one. We have two forces on this member. We have two forces. This is 10 ton. 10 ton. Dimensions are actually in my notes these are feet, but I'm gonna write like these dimensions are meter. Okay, I'm using an American book. No worries, this is, and this distance for each distance is 30 meter. Okay, so here the question is, as you can see, the supports and the dimensions here. For example, I'd like to let me see. This one. I'd like to have FBC, FBE, and FGE. Okay. I'm looking for only these three member forces, not all of them. Use method of sections. Okay, method of sections. Here, when we get the structural system, what are we doing first? We are calculating support reactions. Okay, it's regardless of the methods selected. Okay, firstly, we are gonna calculate support reaction. To do that, let's write the reactions here. Here we have one reaction, and here we have one more reaction. Here we have one more reaction. Okay. What is it? The first one is, for example, I'd like to use the same A. This is A, word horizontal A, horizontal G, vertical G. Okay, let's calculate the support reactions. Let me write them here. Total mg equals 0. Okay, here this is HA, rotates the system in this direction. Assume that is positive. HA times 20, and 10 rotates the system in the same direction. 10 plus 10 times the distance. Distance is like 45. Okay, 30 plus 15. 30 plus 15, and plus 10 times 60 equals 0. Let me make this calculation with my calculator. This one plus this one equals 20. Yes. HA is minus okay, the real direction of this HA is the opposite direction, but we are using this negative sign here, no worries. Okay, let's write the total M A equals 0. Here we have a HG rotate the system in this direction. Let's assume that it's positive. HG times 20. HG times 20. Okay. We have vertical G here. It's in the same direction with the point A. There is no moment for VG. Okay. Let's do this calculation for these tens, minus 10 times, 45 times 10 times 60 equals 0. That's correct. There's something wrong. No. It's same, I think, over 20. Okay. HG is okay. HG is also positive 52.5 ton. Let's write them to the sketch here. HG is this is minus. Okay, vertical G. To calculate the vertical G, we can write the total Y is 0. Total Y is 0. In the system, let's say vertical G is in the positive direction, minus 10, and again, one more minus 10 equals 0. Vertical G is 20 tons. This is 20. Okay. Now we have the all support reactions at the moment. So we are looking for FBC, BE, GE. So the members are here. This one, and this one. So what we are going to do? We cut the system, a line, for example, here, pink. If we cut the system in this direction. So we have two members here, the right-hand side and the left-hand side. Okay, we have right-hand side and the left-hand side. So we can select one of it, left-hand side or right-hand side. Then we are gonna write equilibrium equations on that cut piece. Okay. So what we can do here, we can, let's close this part. We can take the right-hand side out, or left-hand side. Which one is better? Let me see first. Okay, let's total ME. Okay, let's write the right portion and left portions here. Here, what I have. Just a second, I couldn't draw it well. Let me draw it just a second, okay. Okay, here what we have. Okay, this one is. Okay, we cut the system, so we are looking for these forces. The first one is this. We don't know their direction. That's why we always assume that positive. F, G, E. Here I have one more and one more here. F, F, B, C, and F, B, E. Okay, this point is E. Okay, we cut the system, we split it two pieces, and then we can write the equilibrium equations. For example, I have now the left piece. I'm looking for these three forces. Now, if we write total moment 0 according to point E, that means total. Let me change color. Total ME0. For example, this is the point. So these are the unknowns. We have three unknowns. So the moment of these two, this one and this one, around point E is 0. Only we have FB. So we can calculate FB from here easily. Let's do it like that. So FB times the distance, FB times, sorry, FBC, this is FBC, FBC times height of the truss, FBC times 20. Okay, and then what I have more minus rotates. This is the positive direction according to my assumption. This one times 20, and the moment of this positive, this one around point E is 0, but I have vertical component. This rotates the system in the positive direction. So this is 20 times 30 equals 0. So let me calculate this part here. This is minus times okay, or 22.5. Yes. FBC here is 22.5 tons. Okay, we have just calculated easily this FBC. Now we know FBC from now on. Now, we need to find another point, easy point. Let me see. For example, we can write the moment around this point, the point B. Because if we write the moment according to point B, as you can see, FBC and FBE will be 0. So there is only FGE. So we can calculate it easily with FGE. Let's do it. Let me write that equation here. Total MB is 0 here. These are 0. This is 0. Only we have these forces, FGE times 20. And also they are in the same direction, positive 52 times 5 times 20. These are in the same direction, but 20, these rotate system in this direction, but 20 rotate system in this direction. It's minus 20 times 15 equals 0. So let me calculate this one. Okay, over 20. FGE is minus 37.5 ton. Okay, we have this one. Is it correct? Let me check it. Yes, it's correct. Now what we have, we are gonna calculate FBE, the last one, the FBE, this force. Okay, we know this guy, we know this one. Okay, we are using the left piece at the moment. Let me check, is it easy to calculate with left one? Yes, actually. Let me change this location here. I don't want to change the page because all the sketches are here. Okay. Go to this part from here. Okay, let's calculate the total MA. Total MA. For example, the A is here. If I take a moment according to this point, okay, FBC has 0 moment, and FBE we know FGE, there is no problem. Let's do it. Total MA equals 0. At this time, it looks very complicated to you. Maybe you can ask me, oh, how do you decide this point or this point? When you solve a few examples, when you practice it, you are going to understand which point you have to do. I can select any point here, no worries, any point. But what I want to do, when I select a point, I would like to cancel some moments because I don't want to make more calculation. That's it. For example, here I'm using MA. Here is the alpha we have. Let's write the equation here. MA. We have this bottom part. Let's say this bottom force rotates the system around A in this direction. Okay. Times the 20. That's okay. I have the vertical force, but vertical force has 0 moment around point A because they are in the same line. So what we have more? FGE. minus or positive minus 37.5 times 20 times 20. Okay, I did this one. Now, where am I? I'm here. There is no more load. There is only FBE. FBE. I need to calculate the vertical and horizontal component of FBE. Horizontal component of this FBE has a 0 moment on point A. So what I need, only vertical component. FBE rotates the system in the negative direction according to my initial assumption. So minus FBE. Okay, FBE. Let me check dimensions. I need this angle. So what we need, this is 20. This is 15. Let me check the hypotenuse over there. Here is 25. This is 25 meter. This is the angle. So what I need, I need the vertical component. That's why it's the sine component. Sine. We are going to use sine alpha. That means 20 over 25. This is the force times distance. What is the distance? Distance is 15 meter. 15 meter equals 0. Let me check the forces times 20. This part is 1050. Here, this is over 25. Here is 12. Okay. Okay. Yes. Okay, FBE is 25. Let me check again. Yes. From here, you can see FBE is 25 ton. Okay, what I did here, I've just calculated only 3 forces, not all the forces on the members. Okay. Okay, let me summarize what we did here. It looks really complicated, but it's really easy. Okay, I'm not using a ready solution. I'm just solving problems with you because I changed the calculation method here. That's why at the end, I'm just checking the results with the notes I have. Here, what is the differences of this question from the previous one? In the question, I'm not looking for all the forces in the truss system. I'm just looking for three forces according to question. What are they? FBC, FBE, FGE. So I don't have to calculate each one by one. The rule is, firstly, get the structural system and calculate the support reactions. Okay, calculate the support reactions. It's a must. It's not regarding this truss system. You know how to calculate support reaction. Okay, calculate the support reactions first. Okay, keep these numbers here. And then take a look to structural system. Which members do you like to calculate? As you can see in this example, we're looking for this member, and this member. It's good for us. We cut the system, we split the system from where we are looking for the forces. We are looking for these three forces. We cut the system from this pink line. This pink line cut the forces we are looking for, as you can see. So split it two pieces. You can use left piece or right piece. It depends on you. In this question, what I did, I used the left piece with the support reactions. You can solve this problem with the right piece. There is no support reaction. You have only external loadings, 210 loads. Okay, you can do it. I think after this session, please do it for the right-hand side, right piece by yourself. Okay. Okay, what we did, we cut the system and select the one piece. Here, I select the left. As you can see, it's here. Okay, when I cut the members, I don't know the forces on these members. I put arrows. What kind of arrows they are? They are tension forces, because arrows goes out from the joints. I don't know if these forces negative or positive, or tension or compression. That's why I assume all of them are positive, all of them are tension. If I get at the end a negative solution, that means I have a compression force. That's okay, we know that. The sign, negative sign, only shows the direction. Okay. Here, I cut the system and I put here the arrows of the forces that I'm looking for. And I completed the system, as you can see, with dotted line. For example, you can see the point E here. Okay, I'm using this part. I'm using this part. But here, the geometry I'm using as a moment point, this point. It's possible. I know the distance between these points. I can write the total moment zero equation for any point. I know that for each joint location, the moment is zero because there is a hinge at this point. Okay. In the first stage, I did that. I write the total ME is zero. So according to this assumption, as you can see, this FBE and FGE goes to zero because they directly goes into point E. They don't have any moment. Their moment is zero. I mean, so FBC, there is only one unknown here. It's easy to calculate it. Write the moment E equals zero and calculate the FBC. That's okay. Okay, the next stage is MB. I write MB is zero. When I write here MB, total MB is zero. FB is zero, FBC is zero. So there is only one unknown, FGE. I always try to deal with only one unknown. So according to that, I select the points. So if I write total MB, there is only one unknown here, which is FGE, this one. So write the moment equation. So calculate the FGE easily. That's okay. So now there is only one unknown here, FBE. Okay, you can write the moment for any point. I select F not F, M. MA, point A. I select the point A and write total MA is 0. When I do it, FBC goes 0 directly. Its moment is 0. There is only one unknown from FBE, and I can write the moment of other loads. That's it. I did it. There is only one unknown in the equation. So I get the FBE 25 tons. So at the end of the day, what we did here, we used the method of section here. Today we talked about the general rules of the truss systems, and then what provides the stability on the truss systems, how we load them, and we talk about the rule, which is including the number of members and number of nodes. Remember, S equals double D minus 3. There was an equation. If you design a truss system, please provide this equation. We did this, and then we talk about how to calculate the member forces on a truss system. We have two different methods, method of joints, method of sections. When we use method of joints, if we are looking for each member forces on the structural system, we are using method of sections. If we are looking for 1, 2, or 3, whatever, internal forces on the members, we don't have to calculate each member. We can use method of section. We cut the system from the forces we are looking for, 2 pieces, and we consider one of these pieces, and we write the equilibrium equations on this member, as you can see on this example. Okay, what I suggest you try to do the first example, which is regarding the method of joints, which is this one, by yourself. This is really easy. It helps you to understand the method. Please do it by yourself, and please do the method of sections example for the right piece. You know, the right piece is this part. Please calculate these 3 forces with using this right piece by yourself. It helps you to understand these methods better. Next week, I'm not gonna explain these methods again directly. I'm gonna solve you the more complex examples beforehand. Actually, if you take a look these methods, the example or application week helps you to understand. Otherwise, you are gonna try to understand these methods before the final exam. So I know it's gonna be really difficult. That's why try to understand before the exam, especially the application week. In the application week, we can understand more. We are gonna do more complex examples, so you will be good on these subjects. Any questions so far, guys? If no, I'm gonna close the session today, and next week we are gonna solve the examples. Okay, ladies and gentlemen, thank you for your attendance today. From now on, we are gonna start our sessions at 9 o'clock on Saturday mornings. You know this one, 9 to 12. This is better to learn things, and the other side, the remaining part of the day, you can do anything else. Have a good weekend. Have a good week. Take care of yourself. Bye-bye.